Hello. This recording is a presentation of the COLT2025 paper titled Agnostic Learning of Arbitrary ReLU Neuron under Gaussian Marginals. My name is Anxin Guo. I go by Bob. I'm a PhD student at Northwestern University, and this is a joint work with my advisor, Aravindan Vijayaraghavan, who is also at Northwestern University. So let's start from the basics. The ReLU neuron is a building block of modern neural networks, and it is specified by its weight, its bias, and an activation function, and namely the ReLU function. And the ReLU is the most popular activation function. Its full name is rectified linear unit. It is really simple in that it is just the identity function with the negative parts turned into zero. And the ReLU neuron is just a function from n-dimensional input to one-dimensional output. What the neuron does is to first take inner product between the weight W and the input X, and then we add the whole thing to the bias B, and we send it through the activation function, ReLU function, which we call sigma, and this is the one-dimensional output Y that we wanted. And ideally, these parameters, W1 through Wn, and also the bias B, these are the parameters we learn from training samples. So before we go into our theoretical findings, I'd like to first introduce the theory-practice gap in this area. In practice, people use variants of gradient descents to learn gigantic networks, and they work pretty well. But in terms of learning theory, there's no known efficient algorithm that can provably learn even a single ReLU neuron with good fit. So not even the thing we just introduced. And in today's talk, we would just be focusing on pushing the theory a little bit further by specifying how hard it exactly is to learn a single neuron under a specific learning model. And now let's define our problem. This problem is called agnostic learning, and imagine a learning algorithm. The input to that algorithm would be training samples. So naturally, we will give the algorithm access to IID samples, xy, drawn from distribution D, where x is n-dimensional, is often called the features, and y is one-dimensional, is often called the label. And we make the additional assumption that dx, namely the x marginal of the distribution D, is the standard Gaussian. And the output of the learning algorithm is naturally the function from x to y, namely a function that predicts the label based on features. What makes this problem different is that we make no assumptions on y, namely x and y could just be independent from all we know. This is also called non-realizable setting of learning and also called adversarial label noise. So for those who are interested in why they're called these names, non-realizable stand for the fact that it is not realizable. And realizable just means there exists a perfect function f that predicts the label with zero error. Adversarial just means we can imagine the label y to be produced by some perfect function f, and then some adversary comes and just perturbs the label y to be imperfect. That's why we call it adversarial label noise. And the goal of this learning problem is to use a certain number of samples and time, and we want the output function f to have small expected square error. And specifically, we want it to be at most a constant multiple of opt plus an additive epsilon error, where opt is the error of the optimal ReLU neuron. So this expectation here is the squared error of the optimal ReLU neuron. And we note that the number of times and samples that we require is polynomial in both the input dimension n and also inverse polynomial in the additive error epsilon. We further note that a simplification would be to assume that W has norm 1, and also B, the value of the optimal bias, is also known. This assumption is without loss of generality, is because we can just simply perform a search, and this will not use more than polynomial time and samples. And now let's talk about how previous works have studied this problem. Here's the definition of opt, just for a reminder. And previous results have shown computational hardness of this learning problems. So in order for this algorithm to run in polynomial time, we must First, assume something about the X marginal distribution. Otherwise, it will be impossible to produce a polynomial time algorithm. And in this work, we will use the standard assumption, which is to assume is a standard Gaussian. And meanwhile, we must also aim for the error to be a constant multiple of opt plus epsilon, instead of simply opt plus epsilon. And previous works have also studied algorithms for this problem. But prior algorithms are only solving the special cases of this problem, namely the case where the bias B is limited to 0, or positive, or bounded. This means their learning algorithm produces an f that is only competitive against a smaller class of functions instead of all the ReLU neurons. This is why our setting is slightly harder than the previous settings. We also note that all known algorithms are gradient descent variants, which are all CSQ algorithm. CSQ stands for correlational statistical query. This is a model of algorithms that restricts what the algorithm can do. So what it roughly means is that the algorithms can only use sample estimates of the form expectation of y times some function of x. So we view this as a restriction because the algorithm only uses these values instead of doing whatever they want with the samples. Okay, so here's the landscape of what is known until now. Moderately biased ReLUs, aka with the bounded bias B, is efficiently CSQ learnable. And this leads to the main questions of our paper that our paper asks, which firstly, is there a polynomial time algorithm for agnostically learning an arbitrary ReLU neuron? Namely, do we really need to assume the bounded bias property? And the second question is that is agnostically learning an arbitrary ReLU neuron in some sense harder than learning a moderately biased ReLU neuron? And the answer we found is yes. The arbitrary ReLU neuron is polynomial time learnable, but it is not CSQ learnable. Now, here are the main theorems. Notice that how there's a set of problems that are between the CSQ learnable problems and all of the polynomial time learnable problems, and this is called SQ learnable problems. SQ stands for statistical query. Basically, is a restriction on the algorithms again, but is a more powerful set of algorithms than the CSQ algorithms. So our first theorem says there is an SQ algorithm that gets order opt plus epsilon agnostic learning guarantee for arbitrary ReLU activation in the desired fully polynomial time. And this is why we place the arbitrary ReLU learning problem inside the SQ learnable set. Our second theorem is a negative result that says any CSQ algorithm getting the same order opt plus epsilon guarantee must use exponentially many CSQ queries or super polynomially many samples. Formally, the CSQ model is not defined via samples, so this really means queries of tolerance inverse super polynomial. But this doesn't matter in terms of the implications of this finding. And arguably, we have identified the simplest separation between SQ and CSQ learning algorithms. This separation was first discovered by the CKM paper when it is studying pack learning deeper networks. And we also know that more recently, in a paper also appearing in COLT2025, this paper gives a similar guarantee, order of plus epsilon, for a more general class of activations that actually includes biased ReLUs. Now, let's talk about how we showed the hardness and the algorithms. This all came from one. Now, let's talk about how we show the hardness and the algorithm. And actually, both are the same. Are the Mm. Now, since gradient descent on the square laws is a CSQ algorithm, we know that in particular, gradient descent would fail to learn arbitrary ReLU neurons. And in fact, both our algorithmic result and our hardness result stem from the same observation of why gradient descent would fail to learn arbitrary ReLU neurons. So in the next few slides, I will talk about how GD would fail. So technically, a gradient descent update goes into the negative gradient direction. So this gradient is a gradient with respect to the weight W. And once we apply a chain rule, we can actually separate this gradient into two terms. And we note that how, because of the x marginal is a standard Gaussian, and the standard Gaussian is actually coordinate-wise independent, we can actually see that the second term here is parallel to W, which means if we want to focus on how gradient descent updates the direction of W, all we need is to look at the first term here. And the hope is that this first term will help iterate W move towards the correct direction that opt has, which is V, as we denote. And to be specific, the direction of our iterate W will become more aligned with the following conditional correlation. This is just the first term. This correlation is between X and Y on the event that W transpose X is greater than some negative B. And in most cases, the gradient update will be in the correct direction. One example where it will be correct is the case where there is no label noise. Just to explain this picture, the direction W, the current iterate, goes inside the board, and the direction V is somewhere to the top right corner. And if the ground truth is just some ReLU function, then we are just simply looking at the correlation between X and the ReLU function on the event that this indicator is true. This is basically a cutoff made somewhere here. That's why there's a cliff around this right corner. And similarly, if we just manually add some very simple label noise, like this one, I believe is sine of x plus y, then we'll also see the correlation being roughly in the correct direction. Namely, W will go towards the left, go towards the right, and the right is where we want it to go because the ground truth is indeed the top right direction. Now we demonstrate that despite the gradient descent is successful in the previous two examples, there are bad cases where GD would just fail to find the correct direction. And in fact, it would update W in the incorrect direction. So the challenge would come from the highly negative bias regime, namely where the optimal bias B is much smaller than 0. As the bias goes to negative infinity, we claim that most of the conditioned mass, namely the parts where the indicator is true, will be on a thin strip of the input space. And to visualize this, we'll put the previous 3D plot and take a plan view of the thing. Now, this plane just stands for the input space X. The green strip is the thin strip we're talking about. It has width about 1 over absolute value of B. And this is just the result of Gaussian decay. If the condition, if the indicator means we have to focus on the top, on the very top of this input space, then Gaussian decay dictates that most of the weight will be very near the boundary of this indicator. And just focusing on this strip, there is a one-dimensional bad example when the optimal ReLU is very small, is very negatively biased, and it looks like this. There is a planted ReLU to the right, and there is a uniform, very small noise that gives a positive value to all the negative x. So on this one-dimensional bad example, any constant approximation to opt must learn the planted ReLU that goes to the right. That means that if you find something very flat that goes to the left, that is still not a constant approximation because you failed to learn what is on the right. But meanwhile, the label noise on the left actually dominates the correlation between x and y. So if you take the gradient descent, you will be focusing on this green strip. And just on this green strip, it is possible that the gradient update goes to left instead of right. And the CSQ hardness requires something more general. We construct the CSQ hard instance by ensuring for all low-degree Hermite polynomials HE sub k, the correlation between y and HEK of x is uninformative. So what we have above is essentially a special case because the first Hermite polynomial is just x. So this correlation that gradient descent provides is a special case of the CSQ algorithm. Now let's come to our algorithm that will succeed on this bad instance. So we apply a two-stage strategy. The first part is what we call thresholded PCA. It gives a coarse estimation of the optimal ReLU's direction. And the second step is called reweighted projected gradient descent, and it serves to refine the estimation that we got in a gradient descent-like fashion, but it does something slightly smarter so we can avoid the bad case. So thresholded PCA produces the top eigenvector of the following matrix. This is just the normal variance of X, but with the indicator that Y is at least some constant, or not constant, 1 over B above, away from the X-axis. Our algorithm has two stages. The first one is called thresholded PCA. It gives a coarse estimation of the optimal ReLU's direction. And the second part is called reweighted projected gradient descent, and it refines the estimation in a gradient descent-like fashion, but it does something smarter to avoid the bad cases. Thresholded PCA outputs the top eigenvector of the following matrix. So this is just the covariance matrix, but conditioned on the fact that Y is large enough. So this is in an effort to filter out the noise that is very close to zero, as in the bad example we had. The output vector of this algorithm is a constant distance away from the target direction V. And by constant, we can make it arbitrarily small, like 0.001. And this is the non-CSQ step in our algorithm, because this expectation here is not simply just a correlation between Y and some function of X. And the second step, reweighted projected gradient descent, refines the estimation in the following way. It shifts the Gaussian center from the origin to some point along the current direction W. And the new Gaussian center would be closer to the optimal ReLU's positive region, and we are roughly back to the moderately biased case. So this is exemplified by this plot here. Originally, we are centered around the true origin, and then with some estimate W, we can shift the Gaussian center along W, and we ended up at somewhere that is closer to the decision boundary of the actual ReLU. And now when we look at where most of the actual weight is focused on, this will be a wider strip, and the actual ReLU on this strip will be not as biased as before. Therefore, it will not cause the problem of the one-dimensional bad example. But we further note that this version of gradient descent finds the correct signal only when W is close to V to begin with. So if you imagine the direction V to be almost perpendicular to W, then no matter how long or how far you shift the center along W, you will not get closer to the decision boundary of the optimal ReLU, namely the red region. So yeah, this is basically our main results, and thanks for your time.